All right, if you've got condensation happening on a pipe, and you can align the pipe either horizontally or vertically, which one do you think will result in better heat transfer? So if you want to be bold, go ahead and leave your guess down in the comments now. Or if you want to be big brain, you can just wait to the end of the video when you get the answer and then post your guess in the comments and everybody will think you're a genius who knew it the whole time. So we're given in this problem that we've got pressurized saturated steam at 60 degrees Celsius. And we know it's pressurized because otherwise steam would normally be saturated at 100 degrees Celsius. We've got a pipe that's at 40 degrees Celsius. It's 1.5 meters long. We've got a mass flow rate in kilograms per hour, which I'll convert to kilograms per second. What we're trying to find is how much heat transfer is actually going from the steam to the pipe, and then what diameter of pipe is going to be required if the pipe is horizontal versus if the pipe is vertical. And because we want to see actually which of those actually does better. And we'll know which one is better by the smaller diameter. Smaller diameter means less surface area and cheaper because it's smaller. So easy part first, the rate of heat transfer is just going to be the mass flow rate of water times the amount of heat lost by each unit of water. So I'm calling this HFG prime. And HFG is not just the latent heat of vaporization, which you may remember from your thermodynamics class. HFG, latent heat of vaporization, is the amount of heat it takes to go from liquid to gas, or vice versa, right? It's the phase change amount. In thermodynamic steam tables, this is the difference between H of liquid and H of gas. That difference is HFG. The reason that this problem is a little bit different, that we have to modify this amount, is that our steam is at 60 degrees, but the pipe is at 40 degrees. So after the phase change happens, when we go from a 60-degree gas to a 60-degree fluid, the fluid cools down an additional 20 degrees to 40, so that is extra heat. So there's a big chunk of heat loss going from gas to liquid, and then a small extra chunk of heat loss going from a 60-degree liquid to a 40-degree liquid. And the equation in my textbook is a little bit more complicated than the equation in some other textbooks, but I think it is a little bit more accurate, so I am going to use it. And the reason it's a little bit more complicated is that this involves the Prandtl number and the Jacob number. You've probably seen Prandtl number before in other heat transfer projects, but the Jacob number is almost certainly new. This is just Cp delta T divided by HFG. And so if I rearrange this equation, it'll now actually look probably pretty similar to the equation that's in other textbooks with the 0.683 term, just with this extra little adjustment based on the Prandtl number, and as in the amount of heat that is used is a little bit different based on temperature. And the Prandtl number changes based on temperature. So I'm going to have to go back to my material properties and look up the Prandtl number for the liquid water, and all of my liquid values that I look up in this problem, I'm going to be using the film temperature, which is the average between 60 and 40. So 50 degrees is my film temperature. Every property for liquid, I'll look up at the film temperature, 50 degrees. I get a Prandtl number of 3.55. And while I'm back there, I also need Cp, 4.181 kilojoules per kilogram. And HFG, now this will be for the gas, because HFG, this is the phase change. The phase change happens at exactly 60 degrees, so I need HFG at 60 degrees. Plug in all the numbers. HFG prime, the modified latent heat of vaporization, 2411 kilojoules per kilogram. And this is just a little bit more than the 2359 HFG, and that makes sense. It should be just a little bit more. The amount of heat it takes to do a phase change is gigantic. The amount of heat it takes to change by 20 degrees, right, is really small. It's just an extra couple of percent. So now we can plug in to find Q dot, which is the rate of heat transfer. We do the mass flow rate times HFG prime, the modified latent heat of vaporization, 8.03 kilowatts, or if we wanted that in watts, 8,030 watts. That is the amount of heat that is going from the steam to the pipe. And we're going to need that to find the surface area of the pipe. So we can just use regular Newton's law of cooling. Q dot equals HA delta T, the regular convection equation. We've got Q dot. I'm putting 8,030 watts. We don't know H. Surface area. 1.5 is the length of the cylinder. Pi times diameter is circumference. And then the delta T is going to be the 60 minus the 40. And so we don't know in this equation either H or D. So I'll kind of isolate those two terms together and see that HD is equal to 85.2. So for this first problem, I'm going to solve for the horizontal pipe. And I'll just go to the FE reference manual for the easiest possible version of this equation, which is not to say that it is an easy version of the equation, just easier than you might find in some other textbooks. And the FE reference manual is written in form of the Nusselt number, which is HD over K. So HD over K is 0.729 times this big pile of junk, all raised to the 0.25 power. So there's a lot more stuff that we're going to have to look up in the steam tables to finish this equation. And it's important to note maybe at this point that this equation, right, is big, crazy, nasty, that convection equations in general, and this condensation equation in particular, these are not derived from first principles. Like, nobody solved for what this had to be just from basic knowledge. All of our convection equations are approximations based on experiments. We've conducted over hundreds of years, many thousands of experiments, and researchers perform curve fits to find equations that fit our experimental data. And this is why you're going to find so many equations in your heat transfer textbook that have factors like 0.729 times this. It's just the equation that fit the curve. And this is why when you see equations in different textbooks that don't match, like they have a different coefficient or a different power, that's usually why. It's just a different scientist looked at a different grouping of experiments and came up with a different curve fit. And final answers may end up being off by 10, 20, 30% sometimes. So as a student, just make sure that you actually note sort of where you got your equation from and check the assumptions to make sure it's valid. But if you're solving this in industry, you might want to actually look at different versions of the equation and really look at which experiments these curve fits are based on to find out which one is actually most similar to your use case. All right, so let's look up some numbers here. We've got density for the liquid. We've got a viscosity term. We've got a KL term, which is in watts per meter Kelvin. And again, all of these are being looked up at 50 degrees Celsius, the film temperature, since they refer to the liquid property, not the gas. And now, since I was able to solve for HD up in the Newton's law of cooling equation, I'll keep HD on one side and multiply KL over to the other side. So that's why this 0.644 on the outside of the equation in front of the 0.729. Otherwise, plug in all of the numbers. I had to change CP instead of 2411 to 2.4 million because when I plugged in power earlier, I used 8,030 watts instead of kilowatts. So that means I need CP in joules per kilogram, not kilojoules. So I'll take the coefficients and divide them over, raise both sides to the fourth power to get rid of the 0.25. Then I can take all the denominator terms and multiply them, take the numerator terms, divide, and then take the cube root of the whole thing to get d by itself. The diameter for the horizontal pipe, 0.00692 meters, which is about 7 millimeters. So in order to get the amount of heat transfer, we would need a 7 millimeter diameter horizontal pipe. Without a frame of reference, that's not really very meaningful, so I guess we'll go up and find the diameter for the vertical pipe next. We're still starting off the same way, Newton's law of cooling, HA delta T. We get HD is 85.20. That's the same for horizontal or vertical because it's the same amount of heat transfer. The FE reference manual does have an equation for a flat vertical surface. And so I'm going to go ahead and apply this, but in addition to this being flat, there's actually even another catch that the FE reference manual doesn't tell you. But if you look up this equation in other textbooks, you will see it a lot more obviously. So I'm going to go ahead and use this equation for now. But at the end, I'm going to have to come back and we're going to have to adjust it a little bit because it actually does not fit our circumstance very well. So Nusselt number HL over K equals 0.943 whole bunch of junk in the middle times up to the 0.25 power. So these are most all the same liquid properties we already looked up from before, so we're just plugging in a different set of numbers. This time though, notice that diameter is not in this at all, right? This is all based on length because, again, this equation is for a flat vertical face, not a pipe. So I'm just going to solve for H by itself, just the convection coefficient. So plug in all the numbers. There's 1.5 is the length, right? That's the length of the pipe. So I'm assuming that it's a 1.5 meter tall flat wall. And making this assumption, plugging in all the numbers, I get 4152 for H, which then as D is equal to the HD, the 85.20 divided by H to cancel out H, I get a vertical diameter 0.0205 meters, about 2 centimeters. And all right, that was a pretty nasty equation with a lot of calculator work, but what's wrong with it? So there's actually two assumptions that we made when using this equation. The first is that the surface was actually flat, not round, and we need to justify that assumption. The second one, which the FE reference manual doesn't tell you, is that this equation only applies to laminar flow. And at first that's almost sort of weird, like what flow, right? This is just condensation. Why? We're not talking about the liquid traveling. And that makes sense for a horizontal pipe, right? A horizontal pipe, when you have condensation, it just falls off of the pipe after it's a liquid. Even if it condenses on the top of the pipe, it rolls off the side and then falls off. So that is what's nice about a horizontal pipe, is that the liquid just falls off. It doesn't flow along the pipe. But for a vertical surface, when you have water condense on the top, as it falls downwards, it's flowing along the surface of the pipe. And so all of the water that condenses all along the surface, it's all flowing down in a sheet of liquid, like in a film. And so if you just have a tiny amount of water, then the flow will be very small amount of flow. It will be laminar flow. But if you get more condensation happening, the first transition you'll get is to wavy laminar flow, where essentially you have so much water flowing, it's still smooth, but there are ripples, right, on the flow as it moves downwards. And these ripples kind of allow the water to flow horizontally, like further away from the wall, closer to the wall. And that helps heat transfer. It increases heat transfer more than regular laminar flow. So if our flow is in the wavy laminar region, our value for H will be too small. It will actually be, there'll be more heat transfer than we're accounting for. And in fact, if the flow is even more than that, if it's turbulent flow, then our value for H might end up being way too small, right? It'll be a lot more than that because turbulent flow does a lot more heat transfer. So first we can verify whether it's safe to assume that the surface was flat. So in order to model a vertical cylinder as a flat surface, we need the diameter to be very big, right? We want the diameter to be large enough that as droplets flow down the surface, that they're not like being wrapped around the edge. Essentially, we're looking at that there's no like surface tension issues. We want the drop to just travel straight down and not to be kind of wrapped around surface. So as long as the diameter is much larger than the film thickness, then this is a fair assumption. We can assume that it is essentially flat. So the film thickness for condensation vertical flow, it's a very complicated equation if you haven't found H, but since we've already found H, there's actually a much simpler version that we can use. 4K divided by 3H. So we got 0.664 in the numerator, the 4152 in the denominator. We get a film thickness of 0.000213, which means that our diameter, the 0.205, is almost 100 times larger than the film thickness. So yes, this is definitely large enough that you could assume that it's flat. If you had to guess where the boundary would be, like where it's not big enough, maybe like 10, as long as it's 10 times larger, maybe 5 times larger would be safe enough. So this is definitely big enough that making the assumption that our surface is a vertical flat surface is a perfectly fair assumption to make, again, because the film thickness is pretty small. It's gonna be a little bit more work to verify the flow is laminar. For this, we're gonna need a Reynolds number. But we don't know velocity. Every version of Reynolds number you've ever seen before probably has velocity in it, because that's usually we're looking at like how fast does the flow need to be laminar or turbulent. In this case, we're going to find the Reynolds number using the film thickness, which is sort of a proxy for velocity. That is, if it's moving faster, then the film will end up being thinner, right? And if it's slower, the film will be thicker. So you can kind of get some information about velocity from film thickness. So REC is going to be the Reynolds number used here. Density of the liquid times the quantity, the difference between density of liquid and gas, gravity, delta cubed over 3 viscosity squared. And now I'm going to make an assumption here that the density of the gas is approximately 0, because comparing liquid water to vapor water, the difference, like the liquid is basically, or the vapor is basically 0 compared to the liquid. So I'm just going to really call this density of the liquid squared. Don't really need to look up any new values. These are all the same values we've already calculated before. I get an REC, right, a Reynolds number of 103. And different textbooks will actually have a different version of this Reynolds number that are either like double or 4 times the other one. So make sure whatever version of this equation you're using, you're going to refer to a chart in the same textbook that uses the same version of the Reynolds number that's on the same scale. So for my version of the textbook that I'm using in the Leinhard textbook, laminar flow only works up to a Reynolds number of about 7. Our Reynolds number of 100 is definitely laminar flow. And so you can see that the linear fit that fits the data in the laminar region goes at around a Reynolds number of 7. It goes down. There's actually like a pivot in the data. The experimental data goes above the curve fit. And so by using the laminar equation at a Reynolds number of 100, our answer on the line is going to be noticeably below the experimental data. And in fact, based on the graph, there's a little visual cue here of about a 10% error. It looks like we have around a 20% error at our Reynolds number. So since all of the condensation and convection equations are sort of made up anyway, they're all just experimental curve fits, I'm going to do my own makeup equation here and say that since our H value is about 20% too low, I'm just going to increase it by 20%. So I take the 4152, multiply by 1.2 to make it 20% higher so that it'll actually sort of fit close to the experimental data. And I get a new value of H in the wavy laminar region of 4982. And now some textbooks will have a whole separate equation. Instead of doing this 20% correction like I'm doing, some textbooks will just have a completely separate equation that you'll use in the wavy laminar region versus laminar region. If you want to do that, you could plug in a whole separate equation. You'll get about this same answer, plus or minus a couple of percentage points. So new diameter based on this wavy laminar flow, 85.20 divided by 4982, I get 0.0171 meters, about 1.7 centimeters. So let's do the big comparison. Diameter for a horizontal pipe, about 7 millimeters. Diameter for a vertical pipe, 17 millimeters, over twice as big. So you get better heat transfer on horizontal pipes, which is why probably every condenser that you've ever seen, think back to your thermodynamics class when you were studying condensers, like in power plants, every condenser had horizontal flow through pipes. They weren't oriented vertically, right? You get much better heat transfer on a horizontal pipe because the water will drop off of the pipe so that new steam can adhere directly to the pipe. On a vertical pipe, all of the condensation that happens at the top drips down the pipe. So at the bottom, the steam doesn't touch the pipe directly. The steam touches the water that already condensed at the top. So that extra barrier down at the bottom presents more resistance to heat transfer. So you have to have a larger diameter to give yourself more surface area to get the same amount of heat transfer. So I know this was a dense, heavy video with big, complicated equations. So I've got my heat transfer playlist linked up here on the screen. You probably don't want to watch another video right now, but click on the playlist and just bookmark it so that later on when you're working on other homework assignments and other topics, you can just come right back to the playlist and jump into whichever video is right at the time.